when we're doing a curve sketching question, I've just listed sort of the headings for the different sorts of things we want to test for to get information about the curve and the shape of the curve. Starting with the easiest ones, because then we have a couple of points, hopefully, and we already have a good idea of where about on the grid the curve is going to go. So if we start with intercepts, we can do our x-intercept by letting y equal 0. And so I'm going to replace y with 0, and I'm going to have the rational function. Now I can take the x minus 2 and I can bring it over to the other side and multiply it by 0, so I end up with just 2x plus 4 equals 0. So 2x equals negative 4 and x equals negative 2. So that's our x-intercept. So that's great. We already have 1 point. At the point negative 2, 0, we have an x-intercept. So we can do the same thing for the y-intercept. If we have a y-intercept, we'll find it by letting x equal 0. So in our equation, we're going to have 2 times 0 plus 4 over 0 minus 2. That gives us 4 over negative 2. That gives us negative 2 for our y-intercept. So therefore, our y-intercept is 0, negative 2. And so we've got 2 points on our graph already. And what I like to do is kind of keep a running graph as I'm working, and just keep adding the information to the graph, because then that verifies further information that you find as you're doing the other tests, and kind of keeps sort of suggesting more and more about the graph. You're just kind of building it as you go. So already on our graph, if we just do a quick little sketch, at negative 2, 0, we have an x-intercept. At 0, negative 2, we have a y-intercept. And that's what we know about our graph so far. Okay, so asymptotes are next. And if we look for a vertical asymptote, then we want the denominator of our function to be equal to 0. And so that means that x would have to equal 2 in order for that to happen. So therefore, we have a VA at x equals 2. Now, I don't think that you guys have learned how to properly find the asymptotes and test them in terms of a curve sketching application. If you were required to find the horizontal asymptotes also, if it did happen to be a rational function that you were given, then we would look here at the coefficients in front of our x's, because the numerator and the denominator are the same degree. And so our HA is just going to be y equals 2 divided by 1, or y equals 2. And so on our axis here on our grid, we've got a vertical asymptote at x equals 2, so that would be going like this. And we have a horizontal asymptote at x equals, or at y equals 2, like that. Okay? So we're already starting to get a good idea of the shape of our curve. You can kind of see on the left-hand side where we've got our 2 points, and then we've got our intersecting asymptotes, that our curve is going to probably be like an upside-down C-shaped curve. That's what I'm expecting, and then maybe another one in the top right-hand corner as well, but we'll find out when we do a little bit more investigating. So the next thing that we want to look into is, are there any critical points or turning points for this curve? And that means that we need to use the first derivative to find that out. Okay, so the first derivative is going to be y prime equals, we're going to do the quotient rule on this, so we're going to take the derivative of the top, which is 2, multiply by the bottom. We're going to subtract the derivative of the bottom, which is just 1, and multiply by the top. And then we're going to square x minus 2 on the bottom. So let's clean this up a little bit. I'm going to multiply the 2 into the first bracket and get 2x minus 4. I'm going to multiply minus 1 into the second bracket. And then I have some like terms that I can add together and simplify the whole thing. So I'm going to have, 2x minus 2x and minus 4 minus 4. So that's minus 8 on top. And on the bottom we have x minus 2 squared. So if I set that equal to 0, I should be able to find any critical points or turning points for this curve. I'm not going to get a solution because when I multiply the x minus 2 squared times 0, it goes away, and it says 0 equals negative 8, which we know is not true. So that just means that there are no max or min points on this curve. And that's convincing me more and more that the shape of the curve is going to be those upside down sort of C and right side up C. It's like a hyperbola, because those types of curves do not have any max or min points. So let's move on and have a look at the second derivative and see if there's any concave up or concave down changes taking place. All right, for our second derivative, we're going to start with the first derivative. And we are going to we can do the quotient rule again, or we could write this, if you prefer, as a negative exponent and just do the power rule there. I'm going to use the quotient rule. It just makes a lot more sense doing it that way for me. So the derivative of the top is 0, and then I'm going to multiply that by the bottom. Now I'm going to subtract the derivative of the bottom and multiply it by the top. On the bottom, I'm going to square my square, so I'm going to now have x minus 2 to the exponent 4. And so here I end up with 16 times x minus 2 all over x minus 2 to the 4th. I'm going to take one of those factors of x minus 2 off, and I'm going to take that off of the bottom also and change that to a 3. So now I have 16 over x minus 2 to the exponent 3. Now if I set my second derivative equal to 0, that's going to tell me if I have any points of inflection in this curve where the curve is changing from concave up to concave down or vice versa. Again, when I multiply the bracket by 0, I end up with 0 equals 16. And so there's no solution again in our second derivative. And so there is no point of inflection, POI for short. And so we can test for concave up and concave down because we're suspecting that we have these two types of curves. And so we'll test on either side of the intercept, either side of the asymptote, and see if we have concave up or concave down, because other than that, we really don't have very much information at all other than our two intercepts and our asymptotes. So remember our vertical asymptote was x equals 2. So let's try a value of x less than 2. We're going to put that in our double derivative, and we're going to see what happens. We have 16 over, let's choose a value less than 2, like 1, for instance. That's going to give us negative 1 to the exponent 3, which is negative 1, so we get negative 16. And that tells us that for values less than 2, the curve is concave down. Let's try it for values of x greater than 2. So for instance, 3, we have 16 over 3 minus 2 all cubed. And that's 16 over 1, which is just 16. That's a positive value, so therefore our curve is concave up on the right-hand side of our asymptote. And so I think we were correct in assuming that our curve, because it has no max or min points, and because we knew that we had our intercepts at negative 2 and negative 2, that our curve is going to look something like this. So if you were asked to do a rational function on your exam, chances are you probably won't be, but if you were, then that's how you would handle it. Very similar to your polynomial function, just with a little bit more information in terms of the asymptotes. So I was asked to do another curve sketching example of a polynomial function. Apparently the bets are on that it's going to be a polynomial function that you're being asked to graph on the exam. So I hope that we're right about that. So let's start by trying to find our intercepts. If we let x equal 0, then the y-intercept is easy to find. The y-intercept is just going to be 0, 0. For our x-intercept, if we want to let y equal 0, then we could common factor an x out of all of the terms in our polynomial function. So we could have an x times x squared plus 6x plus 9 equals 0. And if we factor that again, we have x plus 3 and x plus 3 equals 0. So we're going to get two intercepts because we have two factors that are identical. So either x is equal to 0 or x is equal to negative 3 are our x-intercepts. So the point 0, 0 and the point negative 3, 0. So that's a good start. We already have some points that we can put on our graph. I've got a little grid over here, so I don't know if this is going to be clear enough, but we can put 0, 0, and we can put negative 3, 0, and then we go, oh, and the y-intercept is also 0, 0. So at least we've got those 2 points to start off with. All right, as far as asymptotes go for a polynomial function, we won't have any vertical or horizontal asymptotes because this is a polynomial function and we don't have a denominator, and we need a denominator for that. So we can just say none. And then we can move on to our first derivative. And our first derivative is going to be 3x squared plus 12x plus 9. If we set that equal to 0, we can see if we're going to get any critical points for our max mins. And so common factor of 3, and we end up with x squared plus 4x plus 3 equals 0. If I divide both sides by 3, then the 3 is going to cancel out, so I don't need to worry about that, and 0 divided by 3 is still 0. So on the left, I'm going to factor this. I'm going to break down 3 into 3 and 1 because they add up to 4. And so our factors are x plus 3 and x plus 1 equals 0. That's going to give me two possible critical points, x equals minus 3 and x equals minus 1. And we can put that back into f of x and find the y values also so that we can graph those points on our graph. Here we would get y equals negative 3 cubed, so that's negative 27, plus 6 times 3 squared, negative 3 squared, so that would be 54, so that would be positive 27, plus 9 times negative 3, and that would be 0. So at x equals negative 3, y equals 0. Oh, we already knew that because that was our x-intercept. And at x equals minus 1, if I put that back into the original function, I'm going to get negative 1 cubed, so negative 1 plus 6 times 1, so that's 5, and then minus 9, so y is equal to negative 4 there. So we have another point at x equals minus 1, and y equals 4 down here. Okay. And so now we want to figure out what's happening around these critical points. So we'll just work over to the side here for our first derivative. And what we're going to do is Okay, so I've written our critical points in intervals, and we need to test and see what's happening in those intervals. In the first case, from negative infinity to negative 3, let's choose a value like, I don't know, negative 4. We would get 3 times negative 4 squared, so 3 times 16, and that's going to be 48. Then 12 times negative 4 is negative 48, and then plus 9. So that's going to come out as a positive value, and that means that we are increasing in that interval. Now if I choose a number in the second interval, like minus 2, I'm going to get 3 times minus 2 squared, so that's going to give me 12. Then 12 times minus 2 is minus 24, and then that's plus 9. And that's going to come out as a negative, and that tells us that the curve is decreasing for that interval. And then finally, from negative 1 to infinity, let's choose 0 there, and we'll just get 9, which is positive, and so we know the curve is increasing in that interval. So I'm going to make our graph just a little bit bigger so we can take a look at these actual points on our grid and see what's happening there. So we have negative 3, 0, which is already on there as our x-intercept. Then we have negative 1, negative 4. Is that already on there as well? I think this point here was meant to be, oops, this point here. I'm not sure if I can erase the other one or not. No, I don't think it'll let me. Okay. So we know that we are increasing until we get to the first critical point, and then we know that we are decreasing until we get to the next critical point, and that after that we're increasing, and also we're going to go through that intercept at 0, 0. And so we have a good idea of the shape of the graph now from the max-min points. The only other thing that we're going to look for is point of inflection. And normally with points of inflection for these types of graphs, if we've got our maximum and our minimum points, then the point of inflection usually occurs right in the middle of those two. So we are expecting a point of inflection halfway between those 2 points. So let's see what happens when we look at our second derivative. So our second derivative is going to be 6x plus 12. If I set that equal to 0, and I solve for x, I'm going to get x equals negative 2. And so we have a possible point of inflection at x equals negative 2, and that makes a lot of sense because our max and min points occur at x equals minus 3 and minus 1, and minus 2 is halfway exactly between those 2 points. And so we need to test our intervals again and make sure that this is a point of inflection and that we're changing from concave up to concave down or vice versa. And so what we're going to do is we're going to go from negative infinity to minus 2, not minus 12. And then from minus 2 to positive infinity, we're going to test a point in between both of those in our second derivative. So let's try maybe minus 3. Minus 3 would give us 6 times minus 3, minus 18, plus 12. That's negative, and so therefore we're concave down in that part of the graph. From negative 2 to infinity, let's try 0 because that's easy. 6 times 0 is 0, plus 12 is 12. That's positive. And so that means that we are concave up for that interval in the graph. And so let's take a quick look at our graph and confirm that we are concave down. Oops. Changing to concave up, and that's happening after the inflection point at x equals minus 2. And so That's a bit of a long one because there's quite a few things to go through in these curve sketching questions. This is going to be your biggest and longest question on your exam, I suspect. I think it's definitely worth going through this and making sure that you can do all of these different tests and draw the graph from the results. Hopefully that will help.